Wave-particle duality.
Light, made up of a stream of particles. Sir Isaac Newton was the main advocate for this theory, the reasoning behind it being that the shadows of objects are very clear and sharp. Basically, light consists of a stream of tiny particles that Newton called corpuscles. These particles shoot out like bullets from a light source.
Light? It's a wave. No, not like water waves. Well, kinda, but it's much more complicated. Light waves don't need a medium to travel in and follow a much more complicated path. If we have two flashlights and we point it at each other, we can see the beams of light don't interact, and that means the particles aren't interacting with each other, thus supporting light is a wave. Thomas Young, who conducted the famous double slit experiment, helped to prove this theory. Now, if the particle theory were true, then we would expect to see two bright spots form on the card, but that's not what Young observed. Instead, a bar pattern appeared of alternating bright and dark spots. This pattern can be explained with waves. Light waves travel through each of the slits, creating two separate wavefronts. As these wavefronts arrived at the screen, they interfered with each other. Bright bands formed where two wave crests overlapped and added together. Dark bands formed where crests and troughs lined up and canceled each other out completely. Not to mention, scientists have found that waves bend and refract, and therefore obey the law that light bends and refracts. And in the 1860s, James Clerk Maxwell, a Scottish physicist, formulated the theory of electromagnetism, that light is a special kind of wave, and electric and magnetic, that doesn't need a medium to travel in.
Actually, there is more to the light as a particle theory. Max Planck, in the year 1900, introduced the concept that light must carry energy in discrete quantities. I know, sounds scary and weird. He proposed that these quantities must be units of the basic energy increment, hf, where h is a universal constant known as Planck's constant, and f is the frequency of the wave. Then came along Albert Einstein. He advanced Planck's theory with what is known as the photoelectric effect. When Einstein shined ultraviolet light onto the surface of metals, he was able to detect electrons being emitted from the surface. Einstein's explanation was that if the energy in light comes in bundles, then one can think of light as containing tiny lumps or photons. When these photons strike a metal surface, they act like billiard balls, transferring their energy to electrons. The electrons move along the metal or get ejected from the surface. A lot to take in, I know, but it explains perfectly why light is made up of particles.
No, light is a wave.
Particle.
Wave.
Particle. I know what you all must be thinking. If Einstein said it's a particle, then it must be a particle.
Einstein did introduce the concept of the photoelectric effect, which strengthened the notion that light is made up of particles. However, a weird thing happened. A while earlier, Einstein wrote a paper about special relativity, and in there he talks about light as if it was a continuous field of waves. Huh?
Basically, when it came down to is light a particle or a wave, Einstein thought both. Both is good.
Today, all physicists accept the dual nature of light, in which light is defined as a collection of photons zooming through space as an electromagnetic wave, and it exhibits both properties of waves and particles.
This discovery shined a light on a whole new world of quantum, known as quantum mechanics, which is basically the mathematical interpretation of the composition and behavior of matter based on the wave nature of particles. A scientist named Louis de Broglie predicted that if light exhibits properties of both waves and particles, then particles should be able to as well. Remember how we talked about momentum of a photon? The equation is P equals h over lambda. Any particle with momentum might also be expected to have an associated wavelength.
This wavelength could be determined from the Compton relationship as follows. If momentum equals to Planck's constant divided by wavelength for photons, then wavelength equals to Planck's constant divided by momentum, which can be rearranged to make Planck's constant divided by mass and velocity for a non-zero mass. These are known as matter waves, aka wave properties associated with matter.
Two physicists in the United States named C.G. Davis and L.H. Germer showed that de Broglie's matter waves do exist by diffracting a beam of electrons through a single crystal of nickel. The diffraction pattern was similar to the diffraction pattern of X-rays that was done by W.H. Bragg and his son W.L. Bragg. The diffraction pattern observed was in almost perfect agreement with the de Broglie wavelength calculations. A dude named J.P. Thomas also carried out a single experiment, except he aimed the beam of electrons through a thin metal foil and bam! The diffraction pattern was similar for X-rays. Later on, experiments using protons, neutrons, helium nuclei, and other particles all produced similar results.
The conclusion? Particles have a wave nature. When we say particles, we mean pretty much everything. Baseballs, bowling balls, even me and you. But our wavelengths are so small and barely have an effect, so that we can pretty much ignore it and say that they behave like particles. But subatomic particles, however, their matter waves have wavelengths that are about the same order of the magnitude of the objects they're interacting with. Their diffraction patterns are big enough so we can observe them. They truly have an observable dual nature.
So where can we apply this amazing concept? Microscopes. The resolution of a regular light microscope is pretty limited. A beam of electrons that has a de Broglie wavelength of less than 1.0 nanometers can produce a resolution of approximately 0.5 nanometers. If we could get the electrons to act like how light acts in a microscope, then we could increase the magnification to 2 million times or more. In the words of Richard Feynman, I think I can safely say that nobody understands quantum mechanics. The world of quantum and wave-particle duality is a weird and scary place, and even though we can make pretty accurate predictions using math, we can't really truly say with 100% confidence that we understand what is going on.